Hi guys, welcome to Edify Academy. My name is Abdul Khan, and today we'll be looking at a few disaster management topics for the prelims 2020. Let's begin. We have four topics planned for the day. We have yellow rust, we have the Odisha flood hazard atlas, we have earthquakes, and we also have lightning. Okay, so let's begin with yellow rust. Yellow rust is basically a fungal disease for wheat crops. Okay, it looks something like this. As you can see, it forms in the form of striations on plants, and this has two effects on the plant. Number one is it absorbs all the food that the leaf makes with sunlight, and number two, it prevents the leaf from getting sunlight. So this results in the plant working suboptimally. Okay, so let's look at a few symptoms of yellow rust that we observe. Primarily, they are obviously the yellow striations on the leaves, and their texture is powdery, and these are also sticky. Hence, they are able to attach to hands and your clothes, and they're able to spread because they also act as spores, right? And the primary temperature at which they occur is around 2 degrees to 15 degrees Celsius. That's an optimal temperature for them, and they require high moisture in the air. So the temperature and weather requirement for this fungus to thrive is usually in winters 2 to 15 degrees, and also if you have rainfall in the middle, it's a very good thriving environment for this fungus. And this fungus attacks wheat, that is a rabi crop, which is sown in winter and harvested in spring, right? Let's also look at the types of rust. There are three types that are known. First is the yellow wheat rust, that's a wheat stripe rust, and we have the stem rust of wheat and leaf rust. We also have impacts of yellow rust that includes draining of carbohydrates from the plants, like I mentioned. It also reduces green leaf area, and it results in stunted and weakened plants. Now there is also drastic reduction in the yield. Now this is what we are most concerned about, right? The yield of the plants, because the grains are now shriveled. There's a loss in the total number of grains and in the grain weight itself, because the food distribution system and the food production system is hampered because of yellow rust. Okay, so in India it is spread along three zones, that is the northern hill zone, the northwestern plain zone, and the areas with rain, fog, and dew, because this is what is most conducive, right, for this rust to thrive. Okay, so this is yellow rust. Let's look at the next topic now. We have the Odisha flood hazard atlas. Now Odisha is a state which is affected by floods every year. Okay, so what Odisha government has done is they have taken images of Odisha during the floods in the last 18 years, and they have layered each one over the other, and they have stacked all of that over the current map of Odisha. With this, we are able to understand how a river flows. We are able to understand when floods occur. We are able to understand which areas get inundated because of the floods, right? So it's a very amazing move that was done by the Odisha government. So as you can see, this is the below layer, that's the bottom layer, that's black and white, is the current map of Odisha, and these colored layers over them are the extrapolated data from the maps that they have recovered in the last 18 years, right? So this atlas is based on record of flood inundated areas, and the imagery is captured obviously by a satellite from 2001 to 2018, and the National Remote Sensing Center, that's NRSC of the ISRO, is what is taking a lead in doing this for Odisha. So all the flood layers of 18 years are combined, and they're integrated with the Odisha digital database. So this helps out any policymakers, planners, or civil society groups to utilize this information that has been integrated into the digital database. Now, this atlas will also help authorities in several ways to systematically plan out flood control measures, to control developmental activities on floodplains, to carry out relief and rescue operations, and to plan relief shelters and health centers. Okay, as you can see, the Mahanadi river here has been plotted, and you can see the flood inundation on the image, right? So this is the Odisha flood hazard atlas, a very helpful initiative by the government indeed. Now let's look at earthquakes. So world over, we experience a few 100,000 earthquakes, and India is prone to a few thousand earthquakes every year. Out of them, just a few are newsworthy, and the rest are detected by laboratories, and it's just utilized as seismic data, right? So let's just look at earthquakes. Now earthquakes aren't named as such, so we won't be focusing on one single earthquake right now, but earthquakes in general are increasing phenomena, right? This is something that actually affects human life. So let's look at earthquakes in general. So this will also be a revision of your basics of earthquakes, right? So first, the terminology. Let's look at the earthquake itself. That's the shaking of the earth. We also have a fault plane. That's basically a plane of contact between two blocks of rock. Okay, in a very simplistic format. If you can understand the basics, you can extrapolate onto more complex definitions, okay, of earthquakes. Um, Also, the hypocenter is the location of the earthquake trigger. That's right below the surface. Please be very careful. Hypocenter is not on the surface, it's below the surface. And epicenter, this is the confusing part. Hypocenter, epicenter, right? So epicenter is the location of the shock origin on the surface of the earth. That's directly above the hypocenter. Okay, so from the epicenter, the waves or the shock waves originate and they move over the surface of the earth, and we experience it all over. Okay, so foreshock is a smaller earthquake that precedes a larger or a main earthquake. The problem is our scientists are unable to decipher if this earthquake that has just occurred is a foreshock or a main shock, right? So the problem is, if it's a foreshock, we are able to tell the public that this is a foreshock, the main shock is yet to come and it will be more deadly, so kindly evacuate. But because we do not know if it's a foreshock or a main shock, we are unable to tell the public in time, right? So this is one of the problems that we are facing. The main shock is the largest and the main earthquake that we experience, and aftershock is the smaller earthquakes that occur after the main shock, right? And this is because the earth is trying to find the equilibrium because of the earthquake. Okay, so this can go on for a few weeks or even months. Okay, something for you to know. Right, let's look at how the prediction is done for earthquakes. Now, prediction of earthquakes is still a crude science because we're unable to accurately predict when an earthquake will occur where, because the crust of the earth is very dynamic. Taking in each and every factor is almost impossible. Hence, it's a very difficult and a crude science. What we have noticed is that animals, they are able to sense an earthquake occurring. Like, we've had so many examples of farm animals reacting abnormally before an earthquake occurs, and that's something that you really cannot understand or go into. And second is this radon gas isotope. Now, as you know, rocks are made up of many minerals, and uranium is one of them. Whenever there is a small little fracture in the rock, or the rock starts to move, uranium begins to decay. Now, this decaying results in the production of radon gas. So this radon gas is detected by the scientists, and we're able to predict that this rock is in motion and there's a possible earthquake incoming for us. Okay, so one of the prediction method is radon. Now, for measurement of the earthquake, we had two ways of measuring earthquake. One was intensity and the other was magnitude. Intensity was measured by Mercalli scale, and Mercalli scale measured the shaking and the damage caused by an earthquake. It was the intensity that the earthquake produced on the ground. Okay, now, but this intensity did not stay constant from location to location. It varied. Now, for example, if an earthquake occurred in New York City, the damage and destruction is immense. But if the same earthquake occurred in a desert that's barren and without any people around, the damage is minimal because nothing has been damaged in general. Because intensity was a factor that we could not accurately take into consideration, we moved on to magnitude. Okay, so magnitude measures how much energy is released at a place of earthquake, or measures the size of the earthquake source itself. Okay, and now this value can remain constant regardless of the location of the earthquake. Okay, there are many scales that are used to measure magnitude. Let's just study two of them because these two are current and important. The first one is obviously the Richter scale. So Richter scale measures the energy released in the locality by the earthquake. Okay, now the scale is logarithmic and each unit represents a tenfold increase in the amplitude of seismic waves. This feature, which was initiated by Richter scale or by Mr. Richter, was copied by every other magnitude scale started copying this formula. That's a logarithmic scale to follow energy as a tenfold increase in amplitude. Okay, now this has been found to be inaccurate when there are more than one type of crust being involved in an earthquake calculation. Okay, hence the energy and the dissipation and the magnitude, everything differs once the medium of the earthquake differs. So this has been found to be inaccurate, hence we have shifted now from the Richter scale to a moment magnitude scale. Okay, so the moment magnitude scale is based on the total moment release of an earthquake. Okay, that is basically the distance of a fault that has moved and the force that is required to move it. In a more simpler manner, it is a measure of how much work an earthquake does in sliding one patch of a rock past another patch of a rock. Okay, something just for you to simply understand the amount of energy that it requires to slide one rock over another rock. Simple. Okay, now this moment magnitude estimates are about the same as Richter magnitude estimates, but this is only for small earthquakes. When you look at larger earthquakes and we have a larger area of land with different crusts involved, the moment magnitude makes a far better accurate understanding of an earthquake than a Richter scale does. Hence, the moment magnitude scale is more accurate for earthquakes that are measuring more than 8 m. Okay, that's 8 times the magnitude of m1, right? Okay, so this is how earthquakes are measured. We won't be going into any specificity because there are a lot of earthquakes that you can look into. With this general idea, you'll be able to understand and mark a few questions when they come up in the exam, right? Now let's look at the last topic for the day. That's lightning. A very interesting topic indeed. Now this came into news because the Climate Resilient Observing System Promotion Council, yeah, pretty big name, CROPSI, is an NPO that works with the IMD. This NPO has plotted lightning strikes across the country. If you notice 2019 and 2020, we've had a lot of lightning strike attacks on people, and there have been many reported deaths due to lightning, especially in states where they have had unusual number of thunderstorms this year and last year, right? So lightning is a very important disaster that we need to understand. So this CROPSI has taken an initiative to plot lightning strikes across the country so that we are better able to understand and keep ourselves prepared for this attack happening from nature itself, right? Okay, so let's look at the science of lightning. Lightning is a massive discharge of electricity in the atmosphere. A simple definition for it, just don't stress yourself, just keep it simple. Okay, now the origin of lightning is still debated, as in there are many theories of how lightning originate, and there is no one solid theory that we can stick to. Let's look at a few theories and we'll just understand what they are so you're able to mark the right one if it does come up, right? So the first difference in the electric charge between the upper and the lower clouds. Okay, so the top and the bottom clouds, if there's a difference of charge, this charge is immediately neutralized by a huge discharge from either of the clouds. Either of the clouds, as in the negative clouds will be discharging the electrons on towards the positive clouds to equilibrium, or should I say to neutralize the effect of this disequilibrium, right? So that's the first understanding of how lightning occurs. The second understanding of how lightning occurs is when two clouds collide and they rub against each other. This creates a functional discharge between them, as in there's a discharge of electrons from one cloud to another cloud, because no cloud will have the same number of electrons, right? So there is difference that has been created because of the rubbing, first of all, and second of all, there's a discharge between them immediately. So this huge electric discharge is lightning that we see. Okay, so these are the two ongoing debated ideas on how lightning occur. So let's look at the reason for lightning. Lightning that we are referring to here is a lightning that strikes the earth, okay, not the lightning that occurs in the atmosphere. Okay, now earth itself is a good conductor of electricity, right? We have earthing at our homes. That's because earth itself is a good conductor of electricity, and it's supposed to be neutral, I mean theoretically, although it's slightly positive. That's for us to remember. Okay, so earth is a good electric conductor, and if there is a raised or a tall object on the earth, the lightning strikes this object first, because the distance between the earth and the lightning source is reduced because of this object, right? This object becomes a medium through which earth can absorb the lightning. So raised and taller objects like trees, buildings, etc. have a higher chance of conduction of electricity, as it is the shortest route of discharge, right? I think yeah, that should make sense. Now let's also look at climate change and how climate change is impacting lightning and lightning strikes on earth. Areas that are prone to heat waves have a higher chance of lightning strike because low pressure is created in an area that is hot. It induces thunderstorms, and thunderstorms create lightning, and we have lightning strike possibility or chances increasing because of this. We also have pollution, because pollution is basically small particulate matter that is spread out into the air, right? Now this particulate matter is what the water droplet will condense into, and water droplet condensing will create rain, and hence you can have higher chances of thunderstorms. And India experiences thousands of thunderstorms, and each thunderstorm brings in hundreds of lightning strikes. So all of these factors together of climate make lightning a very formidable disaster that can occur. So these are the topics for today. We'll be looking at few more disaster management topics for the prelims 2020. I hope you guys enjoyed the class. Do let me know if you want me to add something else to help you in the visual aid, or add more information on any specific topic if required. We'll be doing more videos in this series on other geographical issues and conservation and environmental matters. Do let me know if you want me to add anything else onto the list again. So I'll be seeing you guys in the next video. Hope you guys had a good class. I'll be seeing you soon. Yeah, bye bye. Thank you.